Hi 213, we're going to finish section 12.1 here talking about the last few congruences and constructions that we have. So we're going to start out with the theorem called the Hypotenuse Leg Theorem. In this theorem, if we know a few pieces of information when we're working with a couple right triangles, we'll be able to say that they're congruent. So if we have the hypotenuse and a leg of one right triangle congruent to the hypotenuse and leg of another right triangle, then the triangles are congruent. So notice that we have three pieces of information that we know that are the same. They both have a right angle, a leg that is congruent to another leg, and a hypotenuse which is congruent to the other hypotenuse. So knowing those three pieces of congruency allows us to say that the two triangles are congruent. So let's move on to some selected triangle properties here. Let's start out with a definition. A line that is perpendicular to a segment and bisects it is the perpendicular bisector of the segment. Right? So this really means that we've got to sketch a picture here for you. That means we've got something like this line segment here. The perpendicular bisector will be the one that separates it into two equal portions, right? And it's got to be a perpendicular, so you can't draw it at an angle, right? It's got to be a perpendicular kind of thing like this, right? Okay, so that is the perpendicular bisector here of this line segment, right? That kind of an idea. So what we can say is that any point equidistant from the endpoints of a segment, so any point that's equally as far apart from these 2 points here, will be on the perpendicular bisector of the segment, right? So a point on here, it's going to be on here because it's equally distant away from these two endpoints, right? But we can actually say this in the opposite way too. If you are a point on the perpendicular bisector, then you are equally distant away from each of the endpoints, right? And this is actually constructed because of the triangles that are formed right here. Notice that the two triangles that are formed when you do this are actually both contain right angles right here. This side right here in the center, in the joining the two of them, the backs of them, the legs here are both congruent, and the hypotenuse are equal because we know that they are equally distant from the endpoints here, right? Because of these sections here. So we are actually making use of the hypotenuse leg theorem in one of these situations here. So let's continue with our properties. And start working with isosceles triangles. So remember, an isosceles triangle is a triangle where we have a pair of sides being congruent, right? So we have this. That looks more like an equilateral, but let's pretend that it's definitely not equilateral and just isosceles for a second, where we have two sides being congruent like this. The angles opposite the congruent sides, that would be this angle is opposite this side, this angle is opposite this side. The angles opposite the congruent sides are congruent. So really what this means is that base angles of an isosceles triangle are congruent. Okay, let's start out with a definition so we can get to our next property. An altitude of a triangle is the perpendicular segment from a vertex of the triangle to the line containing the opposite side of a triangle. So if we just have some kind of triangle like this, right, an altitude is going to be a perpendicular segment from the vertex of the triangle. So let's start here with this vertex here. We drop a perpendicular line segment to the opposite side. So that means this here, that is considered an altitude, right? There are three altitudes in a triangle because I could have started with this vertex here and dropped a perpendicular to the opposite side, right, over like that, right? So that would also be an altitude. You could do the same thing over here, right? You could drop an altitude over to this side, right, to create a little right angle right there, okay? So what we can say is that the angle bisector of an angle formed by two congruent sides contains an altitude of the triangle and is the perpendicular bisector of the third side of the triangle. Okay, so the angle bisector of an angle formed by two congruent sides. Okay, so that's basically like working with an isosceles triangle right here, right? And that would be this angle right here that we're going to be using the bisector for, right? So we're going to bisect this angle here, bisect it, yes, and that's going to contain an altitude of the triangle. So this is going to be the angle bisector here. The altitude of that triangle is contained on that line because notice that you're doing a bisector here. That drops it perpendicular to the other side, right? And this is the perpendicular bisector of the third side of the triangle. Okay, continuing on, here's the actual definition for the altitude. I don't know why they put it on the next slide. We needed it on the previous slide, right? So this is the same definition I just had on the previous slide. But now what we can do is notice that actually in my picture back here that I drew a second ago, right, when I drew all of these little altitudes, coincidentally, didn't it look like they kind of did something funny here in the middle. They kind of met, maybe. That's actually what we're talking about here in this slide. The three altitudes in a triangle intersect in one point. They actually intersect in this nice point right here. Yes? So these three blue lines are the altitudes of the triangle. Notice they start at a vertex and drop perpendicular to the opposite side. They intersect at this nice middle point in here, right? They don't actually have to intersect outside of the triangle, by the way. This one is inside because all of the angles are acute. When we've got an obtuse triangle here where one of the angles measures more than 90 degrees, the altitudes will actually intersect outside of the triangle. And we'll talk more about that later. So let's now work with constructions. So let's construct a perpendicular bisector of a segment. So let's construct this vertical line that actually cuts it in half, right? That cuts it down straight through the middle in this perpendicular way. We'd like to construct the perpendicular bisector of a segment by constructing any 2 points that are equidistant from the endpoints of the segment. So let's go ahead and see a video of this. Discard, here we go.
To construct the perpendicular bisector of segment AB, take the compass and place the pointer at A, opening up the compass a little bit more than halfway. Make an arc above the segment, move the pointer to B, make a second intersecting arc. Now open the compass slightly wider and repeat the process. Pointer goes to A, we'll draw an intersecting arc at B. The 2 points, we have the bottom point is going to be Q, and the top point is going to be P. We'll connect P and Q, going all the way through segment AB to create the perpendicular bisector.
Okay, so that was a video demonstrating how to construct the perpendicular bisector. And we'll do more constructions like this when we're together in class. Let's just finish out our video by talking about a construction of a circle circumscribed about a triangle. So now what we mean by circumscribed is actually the circle that is containing all of the vertices of the triangle. Notice that the triangle, all the vertices live on this circle that's on the outside of the triangle, right? Okay, so that's a circumscribed triangle. And constructing this circumscribed triangle or circumscribed circle, right, when we actually are just starting out with a triangle can be a little bit tricky, but it's doable, right? But we do this by following. By constructing the perpendicular bisectors of any 2 sides of triangle ABC, the point where the bisectors intersect is the what's called circumcenter, right? The circumcenter here, this O point, is going to be the center of this circumscribed circle here, right? The circle that goes around the outside of this triangle. And once we know where that center is, it's then easy to finish the rest of the circle since we'll just have to use our compass to drag it around the outside. Okay, so let's go ahead and watch our last video here for constructing a circle circumscribed about a triangle.
To construct a circle circumscribed about a triangle, we first need to locate and construct the center of the circle. This point will be equidistant from points A, B, and C on the triangle. To do so, we need to construct the perpendicular bisector of 2 sides of the triangle. To begin, we'll open the compass, placing the point at A, and making an arc above and below segment AC. Keeping the compass the same, we'll place the pointer at C, making an arc intersecting the ones we originally just had. The 2 places where the arcs intersect will give us our perpendicular bisector. Taking the straight edge, we'll construct that perpendicular bisector to segment AC. We'll now repeat the process, but for segment BC this time. Placing the pointer at B, we'll draw our first arc. Placing the pointer at C, we'll draw the intersecting arc. Notice this time everything is going to be on the outside of the triangle so we don't clutter up the center. We opened up the compass slightly larger, placing the point at B, drawing our first arc, keeping it the same, placing the pointer at C, drawing the second arc. We'll now draw the perpendicular bisector to segment BC, going through those two intersecting arcs. Label the point of intersection as point O. This will actually be the center of our circle. Placing your compass point at O and opening it up to one of the vertices, that same distance, we're going to construct a circle. We'll rotate the compass about point O. This will create a circle that is circumscribed about the triangle.
And that finishes our video for 12.1.